In this video, we are going to talk about section 11.5, which is base E exponential and logarithmic functions. So we first want to talk about what is E, and that may be something you've heard in the past or maybe not, but E in mathematics represents a number. It's called the natural base, and it is actually defined to be this expression, 1 plus 1 over n to the nth power, as n gets larger and larger. So I took the liberty of making a table of values here so you can see what happens. If I plug in these values for x, we want to see what happens to this expression. So for example, x equals 1. 1 plus 1 over 1 to the 1 power. Well, 1 over 1 is 1, so 1 plus 1 is 2. 2 to the first power is just 2. Similarly, when I plug in x equals 2, 1 plus 1 over 2, so 1 plus a half, 1 and a half, and I'm going to square that, raise that to the second power. I get 2.25. I did this here for x equals 5, x equals 10, 100, 100,000, and a million. And you can see that the number gets bigger, but it starts to settle in here. And in fact, between 100,000 and a million, you can see that the first 4 decimal places are the same for this number, 2.71827 and then 28. And so what I would encourage you to do is, on your calculator, find the exponential e, the number e, or look at it as the natural base. And you may have an e to the x button. And if that's the case, put in x equals 1, because you just want e to the first power, which is e. And then what you get is 2.71828 18, and so on and so forth. It actually keeps going. It's an irrational number, so although it looks like it repeats here, it doesn't actually repeat. Okay? So then what we say is that the function f of x equals e to the x is called the natural exponential function. And it's important to know that the interval from negative infinity to infinity is the domain, and the range is all values greater than 0, so from 0 to positive infinity. And if you want to see a graph, check out page 590 in the book and you'll see a graph for the exponential, natural exponential function. So then when do we actually use this? Well, exponential growth and decay are modeled using this the natural number e, natural base e. So if a quantity p increases or decreases at an annual rate r, compounded continuously, then we have this exponential function here that represents this after t years. So previously we talked about compounding in different time frames. So we talked about yearly compounding, or monthly compounding, or weekly compounding, even daily compounding. But now we're going to talk about compounding continuously. So consider this problem. Suppose you're investing $7,000 into an account that pays 6% interest for 10 years. Find the amount that you'll be given under these different compounding. So let's talk about yearly. So let's recall for our compound interest formula, we have our final amount A was equal to P times 1 plus R over N, and then we raise that to the nt power, right? So this is for compound interest. We are going to use this for yearly and for daily, but then for continuous compound interest, we're going to use this formula up here at the top, okay? So we want to find our A value when we invest $7,000, and our 1 plus our interest rate is 6%, so remember we write that as 0.06 over n. N is once per year, and then to the n times t power, so 1 times 10. So I'm going to put this into my calculator here, and we're going to figure this out. And hopefully you're putting it into your calculator too. And even if you're just doing it to double check that you get the same answer as me, it's really important to know how to be able to do this, because this is not something I would expect you to do by hand in your head, but I would expect you to be able to do it on a calculator. So I'm going to round it to 2 decimal places because we're dealing with money. Okay. Similarly, for daily compound interest, we're going to use the same formula that we use, but instead of compounding it once per year, we're going to do it 365 times per year. And remember, we're going to multiply that by 10 up here in our exponent. So again, hopefully you're going to type this into your calculator. And see what you come up with. It's going to be a little bit more because remember, the more often you compound it, the more money you're going to end up with. So this is going to be 12,754.20. Okay? And then let's do it compounded continuously. So in this case, we're going to put in our 7,000. And then we're going to say e to the 0.06 times 10 power. And when we multiply this one out, it's still going to be more. Maybe not a lot more, but it's still going to be more than if we did it daily. So 12,754.83. Notice we only went up by just a few pennies on this last one, but because we're compounding it more often, this is continuously, this is daily, it does result in more money. Okay? All right, so let's use that formula. I'm going to rewrite it up here. A equals P times e to the RT power to figure this out. So a population of rare fish is decreasing at a rate of 5% per year. If the population started at 11,000 and the trend continues, how many fish will be left in 20 years? Okay, so when we are doing this population decrease problem, some things you need to know. Because we are decreasing, we're getting smaller, we have to put our interest rate, our rate of decrease in as a negative number. So in this case, we're going to start with our 11,000 fish, and then e, we have to put it in as negative 0.05 times 20, okay? And that negative represents the fact that it is decreasing, okay? And so I want you to put this into your calculator, multiply it out, and see what happens. Okay? I'm just going to double check my answer here because I want to make sure I get it correct. When I multiply it out, I get 4,046.67, but that doesn't make sense in terms of the number of fish we would have, right? We wouldn't have a partial fish. So I'm going to go ahead and round that to the nearest whole fish, and then we're going to write fish because we are dealing with fish, and so we need to make sure we have units on there. Okay. All right. So again, bacteria population is increasing at a rate of 9% per year. If the population started at 635, then how many bacteria will there be in 5 years, right? So we're going to put this in here, and we're going to multiply it out. And what we get is 995.8. So again, since we're dealing with, we probably don't have 0.8 bacteria part of bacteria, so we're going to say 995 bacteria. Okay. All right, so that's all for this lesson. We'll see you in the next video.